Yeah, so hi everyone again. Today in this reading group session, we'll be walking through the paper, OpenAI's clip paper from 2021, I believe. Let me just change the night mode so it's easier to read. So, just a quick recap from the previous reading group sessions, and obviously I don't expect all of you to have joined the previous sessions, but just to make sure that it's the context is clear. Just zooming in a little bit, just in case some people might have smaller screens. I don't know why this is showing here. Oh, I think it's the search. Okay, cool. Yeah, so previously, we started with a session about transformers, and we saw the application of transformers in, say, language translation, and how you could employ the encoder and decoder for language translation. And then later on, we talked about some different applications of transformers, not necessarily language translation. So, for example, we explained how we could use a language model an encoder only transformer like BERT to do things like sentiment analysis. And in the previous session, we also talked about, let me open the paper actually, because this is going to be the link between the two, so I want to make sure we have the full context. So this is the paper we walked through last week, where we showed the application of transformer to computer vision, because initially the transformer was employed for natural language processing, but it took a while until it found a good employment in the computer vision world. And we walked through this paper quickly last week to show how a simple patching of an image into like X by X patches, and then adding them, doing some linear projection, and then having a transformer encoder was or proved to be an effective method at converting an image into an embedding in n-dimensional space. So that's kind of like what we discussed in the previous weeks. And today we're going to look at a combination of the two models, the two worlds of language or NLP and computer vision. And this is kind of like what started. I don't think this paper necessarily started it, but this is kind of like the recent trend in multimodal model. So you don't have a model which is only computer vision or only language, but you could mix the two. In, say, for example, what we saw in the generation of image from text, or describing images with text, etc. So this paper is actually very influential, and it's very long. So I think in total it's like, with the result, it's almost 27 pages. So obviously I don't anticipate we'll go through it because it's very, in depth. But it's kind of like it can serve as a good starting point if you want to have a good set of references in computer vision, in particular without transformers. But I would like to focus on this session. So I see someone is requesting to speak. I just want to make sure there's no problem with the audio. How do I'm trying to see how to allow someone to go into stage. Invite. Nope, that's not the one. I never actually learned how to use this thing. Maybe you could type your request in the chat just so I know. Just gonna wait a minute to see if there's any problem. Yeah, I don't see any request to speak, so I don't know what happened. But anyway, if there's any problem, please let me know in the chat. But yeah, going back to the paper, so I want to show you the idea quickly. I mean, the one of the things that is important to know about this paper is that this is kind of like, I would say, a leap in computer vision, because previously, like classically, you would see, things like computer vision learning directory from. So where's that? Where they say, I wonder whether it's somewhere here. So I can't find it now, but the idea, which I kind of like also mentioned in the previous sessions, is that with computer vision model, traditionally many models, what would they do is they bring a massive amount of images, and then they have a predefined set of classes, say 1000 classes, like I think in the ImageNet case, and they train the image classifier to tell you whether this is an image, a picture of a dog or a cat or a lion or a house, etc. And the problem with this approach is that the model isn't actually learning to link between what it sees and the language. So if you want, for example, to have another class, say you had 1000 classes and now you have 1001 class, you have to restart your training from scratch, because the model wasn't actually taught to kind of like learn what the language is. And so all it recognizes is that it takes an image and it tells you, well, this is image class 1 or image class 2 up until 1000. And then you, as the model, try to know that image class 1 actually represent a cat or a dog, etc. But what they showed in this model is that they could actually, if they link the training between the computer vision and language, the model will actually be able to learn patterns. So it's able to see that this is a cat or a dog, or actually both of them, just by understanding the picture and linking it with the basic entities making up an English statement or any language for that matter. So we will see how they achieved this, is by initially what they tried to do is so what they tried to do initially is that they had a model, and they wanted, instead of, before that, what they did was, the basic goal they had is to create a sufficiently large data set. And they talk about the data set they initially considered, and how they have a problem in that the MS Coco dataset and the other visual genome dataset, they are actually small, relatively, just 100,000 training pictures. And the other one, which is sufficiently large, which is the Yahoo dataset, it has 100 million photos, but it doesn't have a lot of metadata. So it has like they have the file names, like sometimes randomly generated, or the title and description are just really camera exposure settings, etc. So they decided to have and after they kind of like filter all these not useful data, the dataset kind of like shrunk to 50 million photos, which wasn't enough for their purpose. So they started by constructing their own massive dataset of 400 million image text pairs, and then that's kind of like I'm not entirely sure what they mean by the public available sources. I don't know whether they use Reddit or Instagram, but similar website, I would assume. And then after that, what they wanted to do is that they wanted to pre-train it on this massive data set, so that they can hopefully they teach a model to link the language and the tech and the vision. And what they initially tried is to kind of like link them directly, and then they realized that this is actually not a good method, because you don't want to teach the model to exactly learn to generate the same text. So say for example that I'm just going to open VS Code here. Say for example I have a picture of a cat, and I describe it as a cat walking in the garden or something like that. You don't want to necessarily teach the model to generate the exact same statement, because that's kind of like spoon feeding the model what to tell you exactly. You wanted the model to understand that this is actually a cat and it's walking in the garden, understanding the concept, not necessarily the exact language you wrote, or the person who had that image wrote the description of the image. So then they eventually, what they did is that so that's kind of like what I described here, try to predict the exact same. Their initial approach wasn't actually very effective, because they tried to predict the exact word of the text accompanying each image. This is a difficult task due to the wide variety of description, etc. So what they decided, later on, is that they wanted to train the model to understand the task as a whole, so the whole of that text statement and the image, and they teach the model to understand them. And this way, the model will be given the enough flexibility to actually understand the statement, rather than be required to generate the exact same text description. So that's one thing. And then the other thing is that they used what is called contrastive loss. So the idea is that one of the best methods, where you could teach someone, like even with a human, say for example if you want to teach a kid, or not necessarily just a kid, maybe even an adult, is by contrastive learning essentially. So when you're told that this is a cat or this is a dog, you start to compare them and you see the differences in how they look, and then you understand, well, this is the way a cat looks like or a dog looks like, etc. So that's what they call contrastive learning, and the CLIP actually stands for, I think it's contrastive learning. I'm just trying to find it. What it stands for exactly. I find it here in the website. So contrastive language image pre-training. So that's kind of like their method. And let's now jump into the model. I don't want to spend too much time on the paper because I want to do a live demonstration today. And you can see the basic idea is that so this is their model here. You can see it in this this diagram, and they have a batch of text and then a batch of images, and then they feed them into an image encoder and then a text encoder, and then what they get is the embedding of each one of them. So this could be like 512 dimensional space, or 1k dimensional space, depending on how large you want your model to be. And then the idea is that each image has a corresponding description here. So you can see this one is Pepper the OSC pup, and then the second image has a matching description in the second text, and so on. And so your goal is to maximize the dot product between the first image and the first text, and the second image and the second text, and so on, and then minimize everything else. So ideally you would expect to have ones over this column here, and then zeros everywhere. Obviously that's not realistic, you're not going to achieve these numbers, but that's kind of like the method. And then you can see that essentially this is kind of like in the paper. If you scroll down a little bit, you will see this is kind of like the pseudocode of how they achieve this. So they take a batch of images, mini batch of you can see aligned images and aligned text, and then they apply them. Just a second to see if there's anything on. Yeah, I see some questions here. So I see a question and an answer actually. So Yeah, I mean, I did not actually check how they actually get the description. I think they just use available sources, so say Instagram or whatever. But let me just see the answer here from Richie and Beam. How that is so 500 keywords search for images that have captions containing they say the text image. So they end up with okay. Well, that seems to be a detailed answer you have here. I didn't actually check the detail to see the correct answer, but that seems to be the correct answer here. Right, so and then you can see here that let's go back to the algorithm here where we see that they get a batch of images and a batch of text, and they apply the image encoder and the text encoder, and then after that they oh, actually one thing I forgot to mention, which is after the image encoding and the text encoding, they also apply a linear I don't think it's very clear in here in the diagram, but after the image encoder they apply a linear mapping, essentially just as kind of like a mechanism to help the model being able to convert the embedding it gets from the image encoder and the text encoder into a unified model space. And they do mention it in the text somewhere, but it's not very clear in the diagram, but you can see it obviously in the code, because you can see that they are doing a dot product between the features they are getting and then the weight for the image and weight for the text, etc. And then after that they take the dot products of both of them, and then that's kind of like their logits, and that's kind of like the loss here. So one thing that is also worth mentioning is that they have a temperature, so they scale down the logit by a temperature, and the temperature decreases with the training. And I assume the idea here is that with time you wanna I mean, I'm just guessing, I'm not necessarily 100% confident of this, but I'm just guessing with time they want to scale down the similarity here, so that hopefully to allow the model to be able to distinguish, to have better distinction between, or contrastive loss between the images the more it learns. So it's just kind of like similar, I would assume, to say the classical method of say simulated annealing from optimization, stuff like that. So I don't think there's a lot to talk about this. So yeah, that's kind of like the basic idea. And again, as I mentioned, this is like a very long paper, so I would encourage you to go through it, because there's a lot of details. Like for example, they tried different vision encoders. So they tried the classical ResNet 50 CNN based model, and they also tried the vision transformer, which we described in the previous session. But I want to show you some application I made quickly for this, to kind of like like I was thinking with myself, imagine I have 1,000 of pictures, could be family pictures, could be like trips, whatever, and I want to be able to search. Like I'm sure you all had this time where you have some pictures and you don't know where that picture you want to remember now is, like in which album, in which year, etc. And you might want to be able to search by description. So I made this a simple demonstration, and it's on GitHub already, so I can share it later for you if you want to experiment with it. But let's walk through it quickly. So what I'm doing here is opening, importing the package. And by the way, it's worth mentioning that there is the OpenAI clip implementation, and there is also the OpenClip implementation. This is under ML Foundations, and I encourage you to use this one if you want to use it, because they have taken this task more seriously. They retrained it, and they have like multiple model variants, and they try different data sets. So they tried the Lion 2 billion data set, etc. So you have multiple variants of the model, as I mentioned in earlier. And let's see what let's restart this, and just wanna show you how to use this one. So the package is available on PyPy, so you can install it with pip install OpenEclipse torch. I have it already installed, so I'm not gonna have to worry about this one. So let's start by I'm using the largest model, so it's VIT Vision Transformer, essentially big G14. That's 14 is the patch size. So every image is divided into patches of 14 pixels, which means the model is able to have better understanding of the image because the patches are smaller. So loaded the model, but if you want to experiment with the different available models, I think it's OpenEclipse list models. So that's going to show you the available models that you can use, and you can read the description of the models here. Yeah. So I'm going to read this one now. So you can see the model. If you look at when I loaded the model, you can see that the model has the vision transformer, and then the other transformer, which is the text transformer. Right. So, and then obviously you might have your own images library, but for this simple exercise, I'm gonna use an image library from a package called sklearn-image. And to give you an idea about the images we're going to use for this, these essentially are the images available. And you can see the picture of astronaut, you can see chessboard, a cat, coffee cup, etc. So these are the images, and the idea of the image search is that we're going to pre-calculate the embedding of all those images, and when the user enters some text description, we're gonna take that query and then convert it into the equivalent or the text embedding, and then try to find the image closest to that embedding in our space, or to be specific, in the n-dimensional unified embedding space. That's kind of like the whole idea behind doing the training a text and a vision encoder together. So yeah, let's see. So yeah, these are the images, and then let's how many images do we have? So 2 4, so that we have 26 images. And then let's see, so now we implement a simple function. And then one thing it's worth mentioning is that as you can see, the images here are of different sizes, so we want to be able to obviously to feed them into the model, they have to be rescaled. So OpenEclipse actually provide you with a function. If you noticed earlier when we loaded the model, it also gives you a function for pre-processing images. So it gives you the model, it also gives you a function, it provides an image, and it also it automatically scale it down and make it ready for feeding into the model. So in this function here, I'm just going through all the images available and then pre-processing them, and then applying using the encode image method from the model that the model provides you. And then that's going to take a while because I'm using the CPU here, I'm not using the GPU, so it's going to take maybe up to a minute. Let's just wait for it. Right, and we're going to see after that. I'm just going to take a look at the shape of the images features, and I expect it to be n, where n is the number of images, and that's the embedding dimension. Okay, so it's finished in 41 seconds. Let's take a look at the tensor, and you can see that if I do the shape here, it's going to be 26. That's the number of images I have, and that's the embedding size. So you can see it's a pretty large model with 1,280 dimensions. And then so now we have all the embedding of these images stored here in this tensor. Now what we need to do is something similar for text. And again, you provide it with a text, and then it uses the text encoder to give you the embedding essentially. And let's try to execute this one. And then you can see now the text is of size. Again, it's the same embedding, obviously, because that's the only way you can unify them. So now our job is simply to to ask the user to provide a query. Then we take that query, extract the text features, which is the embedding essentially, and then we do the cosine similarity between all the between the text query and all the available images. And then after that we show the result to the user. So this is a typical cosine similarity, essentially just taking the text feature and multiplying them with the image feature. But notice that we are also using the scale, which is the temperature we mentioned in the equations here. You notice that it's also multiplying it by the temperature, which is the exponential of the scale, which is the exponential of the temperature. So they provide you with it here in the model, so you multiply by it, and then that gives you the cosine similarities. I don't know what happened. And then after that you just apply a typical softmax to get probabilities between 0 and 1. And then finally the typical arc sort, so you get the images with the highest probability, and then we're plotting the image. We're getting a maximum of 3 images here. Now I think I should be doing this instead. Yeah, so we're showing up to 3 images, and for each images we show the image itself using the indices we find here, and we also show the similarity, which is the probability. So let's see how that works with let's see with this one. Yeah, so my query is man with a tripod, and you can see it found this image first, which is that's exactly what the image is, and the probability is actually 1. And it also I should the probability here is just very low, which means it doesn't match the description here. So I should ideally modify my function here to exclude images with a very low probability. And then let's do a chessboard. So to a chessboard, there were actually 2 chessboards in the image, and you can see it rotated both of them, and the probability is 50% for each of them because they're both chessboards. And then I want to show you another thing here. So let's see, in the gallery here, or the library, I have something that I have 2 images of some book or something like that. Well, actually 1, and the other one is some mathematical equation. So I'm gonna tell it to give me the image which contains region-based segmentation. The image containing region-based segmentation. Let's see if it managed to find it. Yep, it's finding it with a probability of 1, and then these are low probabilities. And then I'm trying the text with the math equations. Let's see. Yep, it found this one, and I don't know why it actually thought this is related. I mean, it's a very low probability, so just 3%. Probably it's a text, so it's taking this part and then thinking this is some text. But obviously this part doesn't really match. But you can see it's really smart. So it's understanding that this is some math equations here. Trying with colors here, and then it thinks that, well, this is the image that is the one which is the best matching. So you can see it's pretty nice. But then let's start to look at some of the weaknesses. So with this image search I'm doing here, I'm just entering chessboard, and then let me try to do something like, let's see if it finds this one, the yellow that's the yellowish chessboard. I don't know whether it's gonna find. Yeah, so you can see it wasn't actually able to tell. The probabilities are still the same here, even though I give the alert. But let's see if I do the colored chessboard. Again, it's not finding anything. Now I'm not entirely sure whether this is because of the model has issues or the images maybe of different format, because I saw, I borrowed some of the code in this notebook from from a notebook from OpenEclip, and they are doing some conversion into RGB. So I'm not entirely necessarily sure this is a bad example, but it could be. But what I know is a bad example is, in this case, I'm gonna show the image containing region-based segmentation text, and it's giving me 100% probability. And then I'm just gonna change this to something like the image containing some random text, and let's see what it does. So you can see it's now just not getting it right. So actually, it did kind of like exclude this because this doesn't contain some random text, but it kind of like thought that this is some random text. I don't know, maybe we could actually think that this is some random text. It's math equations, but yeah, let's see. Let's make it a little bit more random, some random text, blah blah blah. Let's see what it does. Yeah, so you can see that it think that this is kind of like 98% matching this description, which you could tell that it's pretty inaccurate. And yeah, I think this is kind of like a weakness in the model, that it cannot be very specific. But yeah, but other than that, it's pretty. Oh, I think that another thing I noticed is that let's see. I have in the image gallery here. So this one is a man with a tripod, and this one is a woman astronaut with an US flag in the background. Let's try this one. The image of an astronaut with a US flag in the background. It's gonna find this one, I believe. So 99%, 99% probability, which is great. Now I'm gonna just say a person. I just want to see what it finds. I have no idea why it thought this is a person, and this is a person. I don't know even what that is. It just seems. I think this is one of the images where if you look at it for some time, I think this one might actually be a pretty clever one, because I think if I'm not mistaken, in this image, if it's the kind of like mental images, or I don't know what they call them, where if you look in the background for some time, you start to see an image of a person in the background. But still, you might expect that at least it shows one of these images, because this is a person, but I don't know why it didn't find it. But yeah, other than that, it's it's great. Let's see if we do an image with a person smiling. Let's see if it gets the. Yeah, I mean this one is indeed a person smiling, but why is this a person smiling? I have no idea. Yeah. So yeah, that's kind of like the basic idea of what I wanted to show you today. Obviously, there's a lot of information in the paper, and there's a lot of experiments, but one thing that is worth talking about is that this is kind of like a fundamental model where they manage. One thing they mentioned is that they managed to achieve the accuracy of the original ResNet 50 paper on ImageNet. ResNet 50 model on ImageNet with just zero shot essentially. So they took the model after a training and they applied it to the ImageNet, and they managed to achieve the same accuracy of the ResNet 50 model. And many of the in the experiment, they go through many of the kind of like they mentioned that this is not just the only example. They tried it on multiple well-known experiments on computer vision, and they managed to achieve like good accuracy on many of the data sets on the test. And they also mentioned how they, in comparison, a model like the one introduced in LAIT 2017 managed to only achieve like 11.5 accuracy with zero-shot learning. Yeah, so I think that's, let me just quickly walk through this to see whether there's anything else I wanted to share. Best publicly. Oops, I don't know what happened. Yeah, I think that's about it. Don't know whether anyone. Seeing some questions here. Let me just go through them. So I see a question here about the loss function, and so the loss function here again, let me just walk through it again. So they take a random batch. This is kind of like a training where batching isn't actually just used for the sole purpose of improving the speed of training, but they actually need to take a batch because they want to teach the model to distinguish between the different images. And the loss in this case, they have a the diagram here where the loss is kind of like trying to maximize these values in the diagonal of the matrix and minimize these values. So these are ideally, and most of the time, are actually different images with different descriptions. So you would expect the embedding of the first image to be as close as possible to the embedding of the text of the first text, but as far as possible from the other descriptions, unless they happen to be similar. And so you can see the equation here for how to do that is they apply the image encoder into the whole batch. This is, you can see this is a whole batch. This is not just one. So this model cannot be trained on small batches. And speaking of this, I think they mentioned that they tried. So we use a very large mini batch size of 32K. So with this, you teach the model to distinguish between all these images. And then the loss function is the dot product of the image embeddings and the text embeddings. And then they do, they apply a cross entropy loss on the logits, which essentially trying to assume that, that's kind of like the labels here. The labels is essentially from 1 to n. So the ideal goal is that you want the first loss, the first image and the first text to be the first, the first label. So they treat it as kind of like a classification problem, but on the result of the dot product between the images and all the text. Essentially it's just what I mentioned here earlier about trying to maximize the diagonal. So I hope that answers this question. Have they mentioned about the embedding size? Yes, they mentioned the embedding size is in the let's see. Training, we train a series of 5 ResNet and 3 vision transformer. So they mention here different visions, and I think the configuration here kind of like, if you go back to the vision transform paper, they do mention the different embeddings. As a base size, we use 63 million parameter, 12 layer, 512 wide model. So these kind of like the description of the transformers. So you can see this is kind of like, oh, actually no, sorry, ignore me. This is the hidden layers of a transformer. So largest size model to get in the train on. Yeah, I don't know exactly where they mention it now, but you can find details here, and you could also find it in the GitHub page where they talk about the different models and the different, the different sizes they use. And if not, if you don't find enough detail, then you have to go back to kind of like the vision transformer paper. And toward the end, they have like a lot of configuration. Oh, actually, well, here's your answer. So embedding size, the biggest one is like so this one is the original paper, well, this the only paper from OpenAI, but as I said, I'm using, so it looks like what the maximum they trained is 1K embedding dimension, but the one I used here from OpenEclip, the biggest one is this one, which, as we saw in our model, has a dimension of 1280. That's the embedding dimension. But yeah, you can check the paper for more details. I see. Yeah, this is kind of like an answer to the question here. Can you zoom into the code? Could you? Yeah, sorry about that. Might be a little bit late for this. Maybe wasn't very zoomed in. Is there any particular code you would like me to zoom in? Yeah, I think that might be the best thing. So I could post the link to the GitHub page. Image search. So that's I'm gonna post it again on the group, on the channel, or the reading group. But this is the notebook. I might do some updates to it later. Just pasting the link here. Yeah, so yeah, you can find the whole notebook here, and you can play with it. Maybe you can implement your own image search project and share it. But yeah, yeah, so I answered this one, Yep, I don't see another question, so I think we can wrap it up now, but I'm gonna wait for a couple of seconds just in case someone raises a hand or have a final question on the chat. See someone typing. Okay, well, doesn't look like anyone is typing anymore. Cool, so yeah, we can end it now. I don't want to take any more of your precious time over the weekend. Yeah, appreciate you joining the session, and I hope you learned something today. If you have any further question or any interesting idea, please feel free to share them on the channel. And actually, I see someone typing now. No problem, pleasure. Cool. All right then. Thanks everyone, and have a great weekend. And looking forward to see you in the next reading session. Bye for now.